Hi, I'm Josh Peak. I'm coming to you from the Space Telescope Science Institute, where I'm the PI of MAST. I mention that because this is a talk about systems, and it's a talk about technology. It's work that I'm doing very closely with the former PI of MAST, Rick White, so a lot of this is his work. He's a great guy if you haven't gotten to know him. So the talk is called Towards Astronomical Search by Image, the Hubble and Planetary Image Similarity Project. Okay, so how do you find data in an archive? Normally you search by metadata. What camera, what filter, who was the PI, RA deck, that kind of thing. And then maybe you might be able to search for something about your objects. So if you're searching through the Sloan database, imaging database, or whatever else, you could search by STSCI index, some basic shape parameters. But essentially you're looking through tabular data there. But if you, for instance, wanted to find all of the X-shaped boxy bulge galaxies that have ever been imaged, you would essentially have to hire a postdoc, have that postdoc write some arbitrarily complicated algorithm, or, if you're crazy, write it yourself, and then, try to apply that to all the images, and it would take you 2 years. So can we do better than this? This is a question that's going to be really important as we enter the age of Rubin, and of Euclid, and of LSST, and so forth, where we're going to have incredible imaging over huge areas of sky. So I wrote this prototype algorithm. It is very silly. We take an image. This is the magic mountain. We cut it into little pieces. We apply these little pieces and we just feed them through an existing network. That existing network, this is ResNet 50, creates a feature vector. And I can validate this network because I know that the interstellar medium is in fact just about 10% velvet, so that makes sense to me. Then I take this feature vector and I run some clustering algorithm, whichever clustering algorithm you like. I'm using TSNE here. And now I can see that each one of these little boxes is represented by a point in this space. Now I can go look in this space and I can say, okay, I look at this thing, I look at all the things near this point, what do I see? And indeed it's highlighting the edges of this PDR that are being photodissociated by hot stars. I am capable of finding things with diffraction spikes, haha, and I can find sort of weird wispy blue crap, whatever this is. Okay, cool, this is fine. It's a thing that works. It's pretty interesting that it works. We have run more complicated versions of this. We've made like little interactive things, exploring. This is a bunch of HSD postage stamp images, so that was kind of neat. But there are more advanced ways of doing this these days. We've talked a little bit about self-supervised learning. Essentially, in self-supervised learning, you take images, you make some modification of those images, and then you run a convolutional neural network, a multi-layer perceptron, and you try to enforce that the images that are modifications of the same image are attracted, are similar, and then the ones that are different from different images are different. So this is a self-supervised approach where you don't have to have labels. This is really neat because these data are unlabeled, right? I don't have labels for all my boxy bulges. So Earth Science is super interested in this, and we've been working with this group called SpaceML, which are industry professionals, to sort of check this as well. I'll just show you that their approach does kind of work. This is from some images from HST, which I'll talk about later, but this is an image, and these are similar ones to it using this SSL approach. So that's cool. The Zooniverse is exploring this as well. Mike Walmsley gave a talk last week that was fabulous. I'm just literally jacking his slide here with permission. And what they've done is, because they actually have some labels from volunteers, they have a latent space inside their network. Mike has a latent space inside the network he's built, and so he can look at an object and look what's similar to it in that latent space. So this depends on labels, but the labels come from the volunteers. And you can look at images. This is a thing that has been labeled, hashtagged by the volunteers as star forming, and you can see it does show sort of similar images. There's color in the slide, I swear. So you've got the basic idea that this thing is doing a good job. Cool. But the key question to me is, are any of these better than the other? If I change some parameter of one of these networks, is it doing a better job? And how would I ever know? This is fundamentally a question about validation, okay? What does it mean for images to be similar? So what we need is a sample of images with known similarities so we can test, improve, and compare our algorithms. This just doesn't exist, at least in astronomical data. So for instance, if we had that, we could ask a question like, if I said, give me the n most similar images to this image, and you needed to have 0 more images among those n. So I'm like, please give me the top 5 most similar. And you're like, to get to the top 5, I have to give you 6. Then you're well down here, and you're an incredibly good algorithm. But if you said, oh, to give you the top 6 images, I have to give you 60,000 images, this is junk, right? So you can imagine trying to score these kinds of algorithms on this thing as long as you have a set of images with known similarities. Conveniently, we had a global pandemic, I don't know if you know. And what that meant is that many people were out of work. And obviously, I'm thinking about this backwards, it was terrible. And what we did is we used a chunk of change from Space Telescope Science Institute to employ service industry professionals in the area near Space Telescope who were out of work. And we paid them a fair wage using Amazon Mechanical Turk. Happy to have long discussions about this versus Universe versus why you do it one way or the other. But this is what we did. And we had them look at these images and make comparisons. So what we did was first, since we are masked people, me and Rick, is we pulled all the NGC objects from the masked Hubble Legacy Archive. We didn't do any restrictions, so we have lots of different types of objects. These are just things that have structure in them, basically. And we got a bunch of cutouts. So the way we did this in detail is we took an image. These NGC things are elliptical, so they have this nice property where they will tell you where things are. You look at the footprint. And then you make some cutouts. We used 488 by 488 pixel cutouts and get these gorgeous images. Do this over lots of different kinds of images, stellar clusters, all sorts of stuff. So these are different and interesting and variable. And we also use image entropy. Both the global and the local entropy will select images with good contrast, with structure in them. Entropy, Shannon entropy has been shown, especially when you go across scales, to be quite powerful for selecting images with structure. Love information theory. I don't know that much about it. So we implemented this as a citizen science project. So what you do is you present a reference image plus a bunch of comparison images and ask the participants to select similar images. So first, they would, in the first phase, they would review all pairs, selecting all similar images from comparison. So this is sort of a approval voting kind of situation where you're allowed to vote for all of them if you want, or none of them, or whatever. In the second, they would review a smaller subset of closer pairs, and I'll talk about what I mean by this in a minute, selecting the most similar image. And then in phase 3, very, very close pairs, selecting the most similar images. And then we would show them at different rotation orientations so that the users could assess these things, knowing that flips and rotations obviously don't matter to us in astronomy. So this is what the first page would look like. We would present the image 3 times just so it's easy to see, and they would choose which ones they thought were similar. And it was really nice because we got to get on a Zoom call with all these folks and talk to them about what they were seeing and exchanged a lot of emails. It was really cool getting integrated with my local community, who I sometimes still see around the neighborhood, which is cool. And then we would use this to build up essentially a list of votes. So we did this across every single pair. So every image was compared to every other image just one time to either vote yes or no, or vote yes or not yes. So from this, we need to build up some kind of information. Sorry, there are equations. So first, for any pair, what's the similarity? So the pair is an ij pair, so the ith image with the jth image. I'm using this s hat for similarity, given some s votes for similar and n votes against. So if it's shown, we'll consider these symmetric, and it has no votes. No votes for it, then if you don't vote, if you see the pair and you don't vote for it, that's an n. If you see the pair and you do vote for it, that's an s. So here we're using the binomial distribution to show essentially the probability distribution function given some n and some s to number of votes for, number of votes against to determine this probability. But most images are not similar, right? Like sort of in general, if you look at 2 things, they're not similar. And so in some sense you have a prior. So you can put on top of that some power law prior. That's what we're doing here. And that gives you a slightly more sophisticated function. I'm using the gamma function instead of factorial because this is not an integer. And so then you can get some typical expectation value for your similarity given the number of votes and given this alpha. So it's interesting, this alpha is something that you can choose. You can say I have a flat prior, you can say it's very steep, you can make some kind of choice. And what I think is kind of neat here is that we can actually object by object see if the objects are as a whole sort of common, i.e. they're similar to lots of things, or if they're super weirdos. And we can use that as our prior for establishing the similarity of any given object to any particular object. Just kind of fun. So that's what we do in the first phase. You can do this lots of different ways. We've tested the living daylights out of this, but that's what we use as our prior. So now I have this similarity matrix, which is cool, but it's pretty sparse, and there's a lot of extra information you're throwing away. So we want to now go from the similarity matrix to a thing that we're going to call a distance matrix. So let's say this is my similarity matrix, and on the x, and this is one object, my eighth object, and this is my third object, okay? And you can see that this is the similarity that I've given them as a score. But I can also see that, you know, they're both quite similar to object number 0, and they're both quite similar to object number 8. And so that gives me extra information. So I can essentially take a cosine distance between these two. Thank you, Peter, for introducing the cosine distance. Taking the dot product. You have to weight it carefully because there's going to be, this matrix may be sparse. In not all situations do we compare every conceivable pair. And so this is a cool way to actually build up a distance matrix that takes into account this extra information, essentially smoothing out a lot of the noise from the fact that you only have so many votes for any given thing. We take this information, and now we can ask which ones are most similar. Now, I'm not really interested in telling, like, is this galaxy really dissimilar from this nebula, or is it really, really dissimilar from this nebula? I do not care. What I care about is the ones that are closest. And so now we give in a third phase, second phase, and a third phase, we only give them the closest ones. We use the distance matrix to inform the distance matrix. It's a nonlinear thing. So now this is a very hard, right? You look at these and they're very, very hard. And our volunteers, our Turkers, do an incredible job with this. And what you can see is that if you compare the distance after phase 1 versus after phase 2, there's some variability. That's, of course, what you want. And then if you look at pair distance, later on, it gets even tighter. So we are sort of zooming in, we are narrowing in. And you can see this is the PDF, or the distribution function, of all of the distances for each phase. So this is the similarity distance and the distribution of each set of pairs. So you've got the idea of the pairs that we're comparing, pairs that are closer in the later phases. We're spending less time over here and spending more time over here because this is expensive. Okay, so let's analyze the result. The comparison results were analyzed for a final similarity distance matrix between all the pairs of images. We had nearly 1 million reviews for 5 million pairs actually compared with all those different opportunities. And it's really stunning how good our neighbors are at doing this. I mean, it's amazing. They don't get trapped by weird things. I mean, we gave them very clean images, but they seem to be very, very good at honing in on this. So then we can take this final distance distribution, and we can do simple dimensionality reduction tools on this matrix to visually inspect the results and see if they make sense. So that's what we did. So this is a TSV reduction. So I've just taken the space. I believe the colors, I can't remember what the colors are for, I'm sorry. I'll have to go check that out. It's some label that we have. Maybe they're from similar programs. But if you just look at this point and you see what's near it, these are these images. And you can see they're doing a great job at selecting things that you visually would say are similar. If we look over here in this space, you're starting to get to these kinds of images. If you look over here, the interstellar medium, this is of course the best part of the universe, for those who are curious. Here's some edge on galaxies. This is really cool. So we extended this. We worked pretty closely with NASA SMD, who's really interested in data science, artificial intelligence, data-driven programs that are cross-division. So this is working with the planetary division, using the context camera on the MRO. And you can see these really beautiful images. I don't know anything about geology, certainly not about Mars, but these are pictures of Mars, I'm pretty sure. And what's cool about this is that we can test how much fine-tuning is needed by discipline, i.e. if a tool works really well with Hubble data, will it work very well with reconnaissance orbiter data too. So we did the same thing. This is what one of those challenges might look like. And then I'll just show you what happens after phase 1. We're still in the process of computing all of these things. This is going to go by really fast. So yeah, it's pretty stunning. Mars is really cool. Maybe we should all go work on Mars. I don't know. Man, what's that? Whatever. But in any case, it's obvious that our reviewers could very quickly see these textures, compare them, and learn a ton. And this will be really helpful, again, for training these kinds of algorithms. So we're going to release these data in a new system that we built at Mass called Hello Universe, and I'd love for you all to think about contributing. Hello Universe is a suite of curated notebooks The notebooks are designed to teach various different tools in machine learning, in data visualization, neural networks, etc., against data sets that we have that we're holding at MAST. So if you have data sets that are even vaguely related to anything that we hold at MAST, I will happily accept them and ask you to make me a notebook. These notebooks we maintain, we run them under CI, so they always run. And they're a really great way to teach people. If you're a professor and you would like to talk with us, we're very happy to, I mean, you can just download them, but we're also just really happy. I think Alex contributed one of our really good notebooks. That's this one. So this is how we'll be releasing it because we want to think of this as a benchmark, right? We want to show people, hey, here's an example algorithm, and this is the benchmark. This is how well it does. Please contribute your algorithms, and maybe we'll have many notebooks that go with any individual set of observations. Okay, so here's a summary. We collected data from the Citizen Science Project. There's lots of these cutouts. We're going to use this to test accuracy of various different methods. Hopefully we'll have these data out pretty soon. The paper is very close to done. And so we'll publish all these data, and you guys can work against them whenever you like. And we're going to publish them all together, not just the similarity distances that we create, but maybe you can make better similarity distances. It's not completely clear if that's the right algorithm that we showed. And that's that. Now I have 3 minutes. I want to show you something that I think is the next level, which is work by Joe. So this is a summary of this part. I'm just going to show you something that kind of melted my face that was built over the last 3 weeks here at KITP. So this is a chatbot that Joe built that ingested a ton of information from the archive. And I would like you just to watch it do its thing. Because I think this is where we're going now, whether we like it or not. And I think what Joe's shown is that you can build these systems. This is just the very beginning, where you can ask it questions about the Gaia sausage and Enceladus merger, and it will give you, shockingly good answers. Now, the question I have for you, here, I'll let it go for a little while longer. I didn't do any of this. This is all Joe. Joe, raise your hand. There, yes, this is all Joe. Yeah, you're very slow typer, so we have to watch her type slowly. So this is amazing, and the question is it right? And once again, validating scientific unsupervised learning, SSL approaches, is just a generically hard problem. Is this right? Is not a problem we know how to answer. But it's certainly something we want to know if it's right, right? So I'm going to argue that this is a major hurdle in the next few years as we pivot towards scientific chat AI. Now I think she's going to ask you about the meaning of life. Yeah, she asked about the meaning of life. So one of the great things Joe's shown here is that you can condition the network to not answer certain kinds of questions, but I'll leave it there because I don't think that's the... Luckily, Joe knows the answer to that question, so that's good. So I think this is a huge, and I really want your attention on this particular topic. You don't have to care about search by image, but you do have to care about this because it's going to be in your life. This is going to be a major hurdle for us in the next few years as we pivot to scientifically enabled chat, if you want to call it that, AI. This is going to happen. You will be there, and so you should think about this. So the question is, how do we validate these kinds of systems? And it's the same question I asked you before. How do we validate whether these two images are similar? Because it's ill-posed at some level. And I guess a proposal I have that I would love for you to tear to bits is maybe we need a fixed set of, I'm using 20 queries. This is a reference to how the Sloan databases were originally built for you database nerds out there, as a benchmark. Questions like, how does supernovae work? Or please give me 12 references on galactic stellar halo enrichment or whatever. Hard questions that, a graduate student, a postdoc, me, might ask while trying to explore a new field. And figure out how we decide if these are right. Do we do this as a community? Do we do this with experts? What's the right way? So I'm going to leave you these questions because I think they're super hard, and I want answers from you, and I'll leave it there. Thank you. You can also just ask Joe questions for the whole time. I don't mind at all.
Beautiful talk, many questions. About this last thing and in particular, the answer that it gave to the references, it looks like it did okay. But I'm trying to understand how this was trained differently than other things, and I know Joe and I even already briefly talked about this, but maybe you can say a little bit about this, because this is one thing where I've actually played somewhat with ChatGPT to try to, and I'm very confused about, sometimes it's literally making up references, and sometimes it's giving me very well-sourced things about things I understand well, and it's telling me the right things. So.
Please give Joe a mic.
Yes, I used the NetMM to first summary. So this is a very early result, but I've been playing with another approach, which is actually more accurate. So the first thing that I do, I use ChatGPT-4 to summarize 10 papers from the archive. I chose just 10 because it costs a lot of money, so I'm happy to receive money here. Yes. So I summarize those papers, and I summarize them in a meaningful way. So I say, like if you say, the GSE was this, add the reference, but also I link that to the archive link. And then what I do is I take those summaries and then I embed them in this, I guess it's called a lang chain. It's a language chain. So this thing, what it does, it takes all of this text and it puts them in a chain of text, which is the model sees. So when you ask a question to the model, what you're actually doing is like, I'm going to embed this question, give you a vector, and then I'm also going to look at this data and find the most similar text relevant to that question, and based on that text, I'm going to answer. So it's only possible because of the great developments that have been done in the last week by software developers. Because ChatGPT only accepts, 2,000 token, 4,000, very, very small number, but there is a possibility to contextualize the model further by this approach. We're not training the model further, we're just giving a very long context to the model. That's it.
Yeah, thank you, Josh. Very cool. I had also a comment on your very last statement about how do we validate this, and I was thinking, perhaps, it can self-train as it works on Wikipedia, right? So it's just, by users using it, you just can tell yourself, oh, I think this is wrong, and then it's just, the same thing as we do with Wikipedia, but training an AI, right? We know Wikipedia works fine and it self-corrects. Sometimes there are glitches, but it self-corrects by itself. So
yeah, I think what's interesting about this in a scientific context is that the number of people on Earth who can validate some of these queries could be extremely small, and their time could be extremely expensive. So, like what happened at this Civil War battle, like there are, 50,000 people, some of which have a lot of free time to answer that question and do the research. But asking a question like this, is this right, is in some sense, like the answer just is ill-posed. Like we don't even know the answer to that question. Science by definition is at the cutting edge. Right. So I think there's a philosophical change there.
At the same time, if you ask this question, it's because you know something. Otherwise, you won't answer.
It's true.
So, yeah. So there's also, some bias on
that. Yeah.
Hi, yeah, great stuff. I'm interested in what you were saying about like applying the search by image to different domains.
Yeah.
And so I get that Mars is a slightly different domain, but it's still imaging.
Yeah.
And so what I was kind of interested in is, could you apply this to like a big radio archive, say like ALMA?
Absolutely.
And just search by data cube almost.
Sure. Again, it's not clear what your proof. Sure. I now have an algorithm. It literally randomly chooses pieces of data cubes and hands them to you. This is the most similar. You're like, no, it's not. And I'm like, prove it. I don't know how to answer that question. I don't know that this is less similar. So I think maybe the hope is that if that algorithm that I just outlined works sort of in these two contexts, maybe it will be more extensible and require less tuning to move into another context. I think SSL is going to probably be the most powerful here, but I don't know. I guess maybe an interesting question is, if I use SSL and I tune it in a particular way, and then I apply it to this, and it does better in Hubble and worse on Mars, That's pretty interesting, right? That's telling you something about the underlying way in which it's working with images. And I don't have an answer to this question, is I think what I'm coming to as I speak.
Hi, Chris Lovell. Sorry to go back to ChatGPT.
No. That's the most interesting part of this, for sure.
On the validation side,
yeah.
So you said these 20 benchmark questions.
Sure.
What's the good result with that? You know, if it answers one incorrectly, is that sufficient? You know, what are the qualitative metrics that we use to evaluate the answers from this? And in a related way, you know, as soon as you publish these 20 benchmark questions, in some sense, you're making that data public for these, you know, the machinery to essentially learn from. So how do you come up with the 20 benchmark questions that doesn't then just get eaten up by the training, in the training data for ChatGPT?
Right. I was just talking to John about this on the way in. No, at the gym. So here's my thought. So let's say I'm, you know, some graduate student who is yet to be born yet, who is publishing their, you know, Astro GPT-9 system that's supposed to do this better than the one that's currently running in ADS. Okay, and if these 20 queries were established by the community, and maybe they would change over time, they would publish what their results were of those queries. And maybe they would say, you know, we have experts on the team who rate these at this level or this level. I think to me the most important thing is sort of the transparency. I think if there were money involved, like, you know, benchmark, you know, like if this were Kaggle, then this would be a problem. But it's sort of not. And if you can, as long as you say, we're not training on these, but rather we're training, you know, mostly what the training is the LLM, and is, you know, how we ingest every word ever written by any astronomer, and how we balance, I mean, you know, you probably want to balance citations, you want to do all sorts of complicated stuff. As long as I think you're transparent in the text of your paper, then I'm a little bit less concerned that you're just like in there meddling with those in particular things. But maybe I'm too trusting. But I don't have the answer. If there's a better answer to this question, my lord, do I want to hear it.
Check. Mike Wormsley. I'm going to go back to the similarity. This is going to be a good coin toss.
Oh, yes, good. You're the person I want to read the similarity stuff. I'm sure you're going to be my referee, so that'll be great.
Time will tell. I love the big picture of there are many similarity systems. How do we know which one works? Let's have a benchmark. My challenge to you is, do you think there is such a thing as objective similarity between images? And just to kind of ground that, the example you showed of like the galaxy where you cut out different chunks and give them to people, right? That will give you a very different kind of similarity between images as if I take the whole galaxy into another whole galaxy, right? 2 spiral arms look similar, but a galaxy with 2 versus 4 spiral arms, so you might say is pretty different. So,
yeah.
so how does your benchmark generalize in that context?
Yeah, it's a really good question. I don't think there is objective similarity. I do think that the difference between my and you and I think talked about this in one context, I remember, in Santa Barbara a week and a half ago. I do think the difference between, I think what we're doing here is we're building a coarse tool that allows you to sharpen, you know, sort of basic parameters until you get pretty good. When you get to the fine grain, you know, is this truly the most similar to this one? That's where I think things get super squirrely. But I think, you know, if I gave you the top 10 and in truth 7 and 9 were interposed, DGAF, right? Like, it's fine. It's much more about having at least some metric by which to compare these things so that we can see if the method that you're using or SSL or ours or various tuning parameters are generally taking us in the right direction. I want a search by image tool that's functional, right? David Hogg has this line where he says, search can be unprincipled, right? You just have to have a metric of some kind that you're trying to optimize. And if, you know, it violates all Bayesian everything, well, I don't know, if it gives me my result, I don't really care. And so in that sense, I sort of do want it to work, but I don't need it to be perfect. But yes, images, there's no fundamental similarity, it's true.
Thank you.
Okay. Let's thank Josh.